And so we get to chapter 10 of James Stewart's calculus textbook. Chapter 10 is called Differential Equations, which sounds scary, doesn't it? I actually took a course called Differential Equations in college before I changed my major. I still have the textbook on the shelf. Don't frankly remember much from that course. However, I still have the textbook, and who knows, I may torture the world with a set of videos on differential equations before I die. We'll see. You might pray, depending on how you want it to end out. But anyway, the first section of James Stewart's calculus textbook, chapter 10 on differential equations, is called Modeling with Differential Equations. You might remember from chapter 1, we did a little section on modeling, which is not on the catwalk, not that kind of modeling, although I suppose there must be some similarity that I won't explore in my mind. But the real world is messy. This is something that is, I think it was frustrating to me back when I was a Puritan of math. But I got over my purist ways, and I now accept that the world simply is very messy. And therefore, we can often not have an exact equation that gives us the exact amount. In fact, in quantum mechanics, it's all about statistical mechanics. You know, the probability of an average, rather than you can't even tell what the position and momentum of a specific particle is. It may not even exist, and that's the current consensus. Basically, math, when you get this high into the ether, and you're so high in math that you can hardly breathe because there's not enough oxygen up here, you have to start modeling things. And so there's some modeling that's going to take place in this chapter, and we're going to use differential equations to do it. Now, I know what you're thinking. What the heck is a differential equation? Well, a differential equation is an equation that has both a function and one or more of its derivatives in it. For example, f prime of x equals x plus f of x. This equation, see, it has an equal sign in it, has both a function and the derivative of the function in the same equation. Hold on for the ride of your life. Okay, so this is a differential equation. Now, the problem with these are you often cannot solve them neatly. We have to model or approximate them. In fact, the general solutions to differential equations, they're often many and various. I'm not at all looking forward to the next section in this chapter. I'm going to have to draw a lot of little arrows and things, probably. Slope fields is going to be the next video in this chapter, because there are so many possible solutions to certain differential equations. And so that's very annoying. And so computers are very helpful with these sorts of things. But we're going to use differential equations to try to model certain kinds of situations. So what is the solution to a differential equation? A solution is when y equals f of x and its appropriate derivatives can be substituted into the equation and it works. Okay, so let's go ahead and see what we're talking about here a little bit more specifically. So one of the examples in this section is population growth. Not a subject of particular interest to me yet. I don't know, maybe it'll grow on me. Population growth? Anyway, never mind, it's not important. So let's say that the rate of growth of a population is directly proportional to the size of the population. In other words, the more people you have, the faster the population grows. This makes a certain amount of sense. I mean, I had two parents, and they all had two parents, and they all had two parents. So it seems like if you go back a certain number of generations, we're exponentially growing. And that the more people you have, the more people are coming in the hospital, so to speak. Now, this is not an exact thing, right? We're modeling this because there are other factors, plague, for example. But we're looking basically for a situation that's not a perfect, exact kind of thing, but that in general, the change of population with respect to time, dpd time, is roughly proportional to the amount of population you have. And so when we have this kind of situation, all we have to do is stick in a little constant of proportionality, and ding, we have an equation. Again, this is not a perfect equation, but it kind of fits in general. So this is a differential equation. Why is it a differential equation? It's a differential equation because we have a function and we have a derivative of a function, and so it's a differential equation. Okay, so now what kind of I mean, that's all fine and good, but what kind of specific equation might model this situation? So we're looking for a function whose derivative is a constant times itself. Well, how about an exponential function? As it turns out, in the 4th section of this chapter, we're going to find out that that's the only kind of function that can model this kind of a situation. So let's go ahead and try out this as a possible general solution to this kind of situation. So the function of population per time, the amount of population as a function of time, equals some constant of proportionality, capital C, times E, that's 2.718281828. It's a funny number that's important in math, to the KT, where T is time and K is a constant, in relation to it. Okay, so let's see if this works. So what is the derivative of this? What is P prime of T? Well, the derivative of this, this is a constant, so it comes out. And then to find the derivative of this, it's going to be the K. K is going to come out times E to KT. So if I rearrange this a little bit, switch things out, I bring the K out and the C in, then I have that the derivative of the population in relation to time equals a constant times, it's the same thing. In other words, it equals this. Ding! We've come up with a model that works, because with this formula, the derivative as a function of time equals a constant times the original function. And that is, of course, a differential equation, because we have two different levels, as it were. We have the original P of t, and we have the derivative of it, P prime of t. Okay, now, by the way, if you solve for P at 0, so let's stick in t equals 0. Then it's going to be e to the 0 power, which is 1, and 1 times c is c. So at p equals 0, at the initial population, at time equals 0, the initial population, we find out that the constant turns out to be the initial population. And so now, if we're going to do population studies, because we're into that kind of thing, we know that C stands for the initial population. Okay, now by the way, the world is messier than that. So not only is that, as a sign of how not quite accurate what we just did is, there's something they talk about called the carrying capacity. There's usually a point where population growth levels off. It approaches a capacity. There's no more room on the island. If we have any more babies, we're going to fall off the cliff. Or there just isn't enough food, and so people begin to starve, or sickness, or whatever. So K, population people who are into this kind of social science, talk about K, the carrying capacity. And so basically our original formula only works if P is small enough. If the population is small enough, then the rate of change of population is roughly proportional to some constant times the population size. But if P exceeds the carrying capacity, then this is going to be negative, because we don't have enough space, and so the population is going to decline. Or we don't have enough food, or the population is going to decline. It's going to level off. And so we have to somehow factor in this K, carrying capacity, into our formula. And there was a guy in the 1800s whose name escapes me, who came up with what's called the logistic differential equation, which makes that kind of adjustment. Is it precise? Is it exact? It's not exact, but it works in general. And so you can see that this part of it is exactly what we had before, that the rate of change of the population is equal to some constant of proportionality times the size of the population. But this factor is now entered in, where K is the carrying capacity. So we can see that there are two equilibrium solutions. What I mean by that is there are two solutions to this where the rate of change of the population is 0. That's when P equals 0. So when you don't have any people, you're not going to have any babies. I mean, how does that work? I'm not sure. But I think if you think about it long enough, you'll realize that if the population is 0, you're not going to have any change in population. So that's one of the equilibrium solutions. The other one is when the population equals the carrying capacity. That's when we've reached an equilibrium. We've reached the capacity of this population. In that instance, then P equals K, K over K equals 1, 1 minus 1 is 0, and this equals 0. And so those are the two equilibrium solutions, because the change in population is 0 at those points. Okay, little population. Now to something more to my liking, physics, motion on a spring. Do you remember Hooke's law? Hooke's law tells us that the restoring force on a spring is negative kx. What does this mean? Well, there's basically, you have an equilibrium point for a spring, and if you stretch it, doing, slinky, but it's negative because the force is always pulling whatever is the end of the spring, is always pulling it back to the equilibrium point. So x is the displacement from the equilibrium point. So that there's a restoring force on the spring, or on a pendulum, or on something like that, that's always pulling the thing on the end of the spring back toward the equilibrium point. And so basically we have a constant of proportionality k, and we've got an equation, F equals negative kx, right? The restoring force pulling it back to equilibrium equals negative constant times the amount of displacement. Now, here's an interesting thing. You remember Newton's second law, which says that force equals ma, and so ma, the mass on the end of the spring, and its acceleration must be equal to negative kx. Hold that thought. What is A? A is acceleration. And we know from our math and our physics that acceleration is the second derivative of displacement. So displacement is x. The derivative of displacement per time, is velocity. That's the first derivative. And then the second derivative is velocity, change in velocity per time, which is acceleration. So we can now cook something here. We've got the ingredients. Let's do some cooking. So ma equals negative kx, right? The restoring force equals mass times acceleration. And acceleration is the second derivative of x. This is what's called, for the first time ever, a second order differential equation, because we have a function x, and then we have the second derivative of the function, d2x dt squared. Okay, I guess that's how you say that. I don't remember. I used to know, but I'm going to say it that way until someone corrects me. So this is a differential equation. Now, if we were in a physics course, we would go on and say, how can we model this? In fact, I'm sure the book does it somewhere. But what is a basically we're looking for some kind of a function that would model the second derivative of that function being proportional to the negative of the original function. Well, sine and cosine do that. Because with sines and cosines, the second derivative is proportional to x, but with the opposite sign. And so what we're getting into is something in physics called simple harmonic motion. It strikes fear into my heart, but I think I'm beginning to understand it. And it is basically based on this modeling. I think, when I first encountered simple harmonic motion formulas, I was really puzzled by it. This is helping me. It's a model. Basically, we're looking for a kind of equation that fits a particular situation so we can model it. It's not a matter of necessarily strict proof for someone like me, although I'm sure the mathematicians can prove it. But it's more of a matter of modeling a situation. Final slide, and then you'll be done with me. So initial conditions. As I said, there are often many general solutions to a differential equation, a family of possible solutions, as we'll see when we get to the slope field video that is the next in this chapter. But often, maybe usually, we want a more specific solution to a differential equation, one that satisfies some additional requirement. So yes, there are lots of these possible answers, but I want the answer that goes through the origin 0, 0, that kind of additional requirement. And a lot of the problems you'll have in the exercises have to do with joining a differential equation to a specific kind of a situation like that. Where the solution to the differential equation that has slope 5 at this point, those kinds of things. Now, a key example of an additional requirement is when you're looking for the initial condition. Let's say you're doing some physical situation like population growth or something like that, or the motion of something, and you want to know the initial condition, where y of t sub aught equals y sub aught. Aught is a fancy name for 0, t sub 0, y sub 0, however you want to say it. But we want to know the initial condition of it, and sometimes that helps lock a differential equation out of many possible solutions to, ding, the one solution that works in this particular case. So that's a key kind of situation where you're solving for the initial condition, or you're given the initial condition as an additional factor into your problem. This sort of a problem is called an initial value problem, when you're trying to find the initial value of something that is a differential equation. Whew, shoo, we made it. I've been sweating this whole video, but we made it. I don't think I've said anything wrong. And so, ding, we're ready to go with differential equations. I think I'm going to like them, although I'm still a little nervous, to be honest.